Okay, so hello everyone, ladies and gentlemen, and dear fellow developers. My name is Ingela Anderton Andin, and I work for the Erlang OTP team. This talk is about Erlang OTP design, exemplified by our TLS application, or actually it's called SSL for historical reasons. I should also mention that this is a slightly shortened and updated version of my code-beam San Francisco talk this year. Oops. No? Yeah, so firstly, what is TLS? It stands for Transport Layer Security, and it provides three things for a message sent over a computer network. Firstly, data privacy. Only the sender and the receiver of the message should be able to read it. Secondly, integrity. Nobody should be able to tamper with the message on its way through the network. And last but not least, authenticity. We should be able to verify that the client and the parties communicating are whom they actually claim to be. So computer history moves a lot quicker than human history. The first version of the protocol was designed by Netscape in 1995, but it was actually never released to the public as it contained so many vulnerabilities. So it was quickly replaced by SSL 3.0. That was also the first IETF standardized version of the protocol. But also this version of the protocol is considered dead because of the so-called Poodle attack discovered in 2014, which is an ingenious attack where you alter some padding and then you observe different error messages and then being able to decrypt the message. So in 1999, the protocol changes its name to TLS. And TLS 1.0 and TLS 1.1 have some small but important differences from SSL 3.0 to cover security breaches like the Poodle attack. But still, these protocols are vulnerable to other attacks. And it doesn't support, or it has very limited support for modern cryptographics like elliptic curves. And actually all big browsers have stopped supporting these versions in March of this year. So in the computer dark ages in 2008, we got TLS 1.2. It introduces a lot of new algorithms and new extensions to be able to have more secure connections. But it's still also very backwards compatible, letting you use all the old stuff too. And today and into the future, we have TLS 1.3. It introduces new protocol message flow and it encrypts earlier. And it also removes lots of legacy algorithms considered broken. So secondly, what is OTP? You probably all have your own notion of what OTP is. And originally it stands for Open Telecom Platform. But today it's only a brand and the meaning historical. And I think you can all agree that supervisors, design principles, applications, releases, behaviors, that is OTP. But what more can we include? And where do we draw the line? And do we have to? I think as OTP as a box of Legos, with many general pieces, but also some very specialized ones. And which ones we want to include, of course, depends on our problem. But let's focus on the core Erlang. And in contrast to with Java, for instance, that is an object-oriented programming language, Erlang is a functional programming language. That is, the main primitive is a function and not an object. So a function is simply something that takes some input, transforms it somehow, and produces some output. And then we take our related functions and we group them into modules. And modules are just files of Erlang code. And then we take our related modules and we group them into applications. And applications in turn can be grouped together into releases. And the release is aimed to be run on a target system. And then, of course, you can have third-party products like Hex or Rebar to manage it if you want to. Erlang also has a main building block for parallelism, which is a lightweight process. So Erlang processes have their own memory, and they communicate via message passing. And they are scheduled by the Erlang virtual machine. An OTP application is mainly structured as a process tree, where we put supervisor processes at the top, and we have leaf processes that are the worker processes that do the actual work. Worker processes under the same supervisor are related to each other and they have a defined start order, except of course if they're under a simple one-for-one supervisor that has identical but unrelated processes. And the work of the supervisors are to start, restart, and gracefully shut down your processes so that you, for instance, don't get any process leaks. There's also another type of application that has a purely functional API and doesn't define any processes. An example of such an application that is related to TLS is the public key application. So what does it do? Well, the authenticity part of the TLS stack is realized by certificate chains. So that means that the peer has to own the root certificate on beforehand, and then you send the rest of the certificate chain as a message. And then when you have the whole chain, you can have a recursive function that goes through the chain and checks the signatures, the name chaining, the dates, etc., etc. And also the certificates and their associated keys are stored in so-called PEM files. So handling the PEM file format or verifying the certificate chain is given the same input, you will always receive it or end up with the same output. So hence we put this in a library application. The basic design of TLS is a layered one. So at the bottom, you have a reliable transport protocol. In practice, TCP/IP. And on top of that, you have what's called the TLS records, which is the TLS packaging format. And on top of that, you have 4 different protocols: the handshake protocol, taking care of the TLS handshake, the alert protocol, handling errors, change Cipher spec, tells you that, okay, it's time to use new encryption parameters. And then we have the application data layer that handles application data. So if you are coming from an object-oriented background, you would easily map these layers to objects. And also coming from an object-oriented background, people like to think of objects as processes. But there's no such one-to-one mapping, because processes are actually parallel entities. And we want to think of the layers of the TLS stack more as events in our state machine than separate processes. So here is what the basic TLS state machine looks like before 1.3. So I will start with the blue path. So in the hello state, the client says, oh, hello, I know these versions of the protocol and these algorithms. And the server will say, okay, hello, well, let's run this protocol version and these algorithms. And then we go on to the certify state, where they check each other's certificates and exchange keys, so that when we come to the Cipher state and receive the change Cipher state Cipher message, we can start encrypting. And then we encrypt our first message, verifying the connection, and then we can go to the connection state, where we handle application data. So if we take the red path instead, we go directly from hello to the so-called abbreviated state, where we kind of skip most of the renegotiation because we have saved session parameters from a previous handshake on both the client and the server side. And then we can make a shorter handshake and come to the connection state again. And once we're in connection, we can issue a renegotiate that will start the handshake re-over. And this could be interesting for updating the session keys, for instance. So 10 years ago, our first supervision tree for the TLS application looked something like this. So we started off with a one-for-all supervisor at the top, because if we shut down our application, we want all the processes to die. And then, of course, we have our state machine processes. Thus, they rely on a GenTCP connection, so there's no point in restarting them, because if the connection is lost, we have to start from scratch. So they are temporary processes, but they are independent of each other. So we put them under a simple one-for-one supervisor. And then we also had this gen server process to keep track of some global data, such as session data. But since then, we did not only add 4 versions of the TLS protocol, we also added DTLS. So what is DTLS? Well, it's basically TLS over UDP. And yes, that means that application data in DTLS might be lost. But we can't lose the handshake data, because then we can't perform the handshake, so that has to be resent. And if you look at the picture, all the red parts in the picture is the difference between DTLS and TLS. But as you see, all the white parts, they are the same. So to avoid maintenance nightmare, we want to reuse as many functions as possible from the TLS implementation to implement DTLS. But at the same time, we of course want to have different DTLS processes, connection processes, than TLS connection processes, because we don't want any bugs in DTLS to affect our TLS connections, or vice versa for that matter. So our current supervisor tree looks something like this. And I'm not going to go through it in detail, but as you see, we have the top supervisor, and we have a subtree for TLS connections, and another subtree for DTLS. And we also have a subtree for the administrative part now, because we found that we need more processes to avoid bottlenecks in handling global data. And when running Erlang distribution over TLS, we actually bumped into that the GenTCP send primitive is a blocking function. And that means we needed to split our connection process into 2 processes, sender and receiver, to avoid a bottleneck. And this bottleneck is actually much more likely to happen when you run over the distribution over TLS than when you have a normal client server. And also, of course, TLS 1.3 came with new requirements requiring new processes. And on the subject of supervisors, as I said, our connection processes are not related to each other. So when we want to spawn connection processes, we don't want them to wait for each other's init phase. But using the normal start functions of behaviors, we couldn't avoid this. And even if we immediately in our init function act that, okay, it's okay to continue, you would have the supervisor being scheduled out, the connection process being scheduled in, sending a message, supervisor being scheduled in again, receiving the message before it could spawn the new connection, and that is not good. So that is why we use the primitive proclib spawn link to start our processes, and then we use the gen state and behavior enter loop to go into our process loop and avoid this. As I said from the start, we didn't have gen statem, so our processes were gen FSMs. And the code that you see here is some actual code from that gen FSM implementation. And don't worry, you don't have to understand it in any detail. The point I want to make is that the shortest path between a point A and B is a straight line. And using the gen FSM behavior just wasn't helping us to get there. And one problem with gen FSM is that it views all events as Erlang messages. But our events are Erlang messages, messages received on the socket, and also return values from processing the different layers. And you see all the red parts in the slide are places where we work around the gen FSM limitations. But nowadays we use gen statem. And you see these 3 lines of code here and this little help function. It actually does the exact same thing as the code in the previous slide, but now working with the behavior instead of against it. So let's take a look at the difference between TLS 1.3 handshake and the previous versions. All the blue messages in the picture are sent in the clear. All the red messages are encrypted, but the light red messages are encrypted with different keys than the dark red ones. And you can also see that we gain 1 round trip in TLS 1.3 compared to previous versions, and that corresponds to the arrows in the picture. So if we take a look at the abbreviated handshake, we see similar differences. But I would say that the really big differences is not really shown in this picture. And I would say there's like 2 major differences. One is how sessions are reused. The TLS 1.3 mechanism uses something called session tickets and is based on pre-shared keys. And this is totally a different mechanism than the earlier one. And also in TLS 1.3, there's something called early data, so that you can send encrypted application data together with the first client hello. And I think this is aimed at optimizing HTTP GET requests, actually. I'm not going to go into a lot of details of the session reuse mechanisms, but I will talk a little about them. So at the left here, if we start with the old mechanism, you have to save data on the client and on the server side. And this can be quite voluminous. And also there's this 32 bytes of random data that they use as an ID to point to this session data. So in our first implementation, we used this random data as a key into a nets table. But as the data is quite big and can be quite long-lived, we want to put a limit to this nets table. But at the same time, as we don't want it to grow too much, we want session reuse to be done as much as possible. So when we hit the limit, we have a problem actually that we don't know or have an easy way to know, which is the oldest session. So we implemented a shrinking mechanism in the background that would shrink the table gradually. But this still could cause a problem if you have the ability to fill the table quicker than we can shrink it. So when we implemented the session mechanism for 1.3, we kept this in mind. And we use some monotonic data that we can use as an ID into a generally balanced tree. So when we hit that threshold, we can just get rid of the oldest session easily. Now the 1.3 mechanism is very different and doesn't require as much memory as the old one. But we thought anyway that this is important, and actually we're in the midst of rewriting the old mechanism to be more like the new one. Another thing negotiated by the TLS protocol is the so-called Cipher suites. And the Cipher suites in the protocol are represented as one binary. But actually it represents a collection of algorithms. And all these algorithms are used for different things like key exchange, payload encryption, etc. And they can also be used together in different orders. So you get quite a big set of Cipher suites. And also different versions of the protocol have different number of algorithms. And at first we had them as tuples, and then we made them into maps. And OpenSSL have them as strings. Configuring the Cipher suites in OpenSSL would look something like this, or like this magical regular expression at the bottom. So we don't want you to write long lists of strings, tuples, or maps for that matter. So that's why we have these two functions so that you can find out which are the available Cipher suites. And then you can filter them on any part or on any potential part of the Cipher suite. So this example filters out all, it's from OTP 20 actually, and it filters out all Cipher suites that uses RSA as a key exchange algorithm, because RSA as a key exchange algorithm is broken. Actually, it won't be part of the default Cipher suites in later versions. And beneath the line, you can see 4 out of 5 possible Cipher suites in TLS 1.3. So maybe you could live with listing them. But TLS 1.3 and doesn't have any overlapping Cipher suites with the previous versions. And I think the internet will not be TLS 1.3 anytime soon. So I think you still might have use for our functions. Also, I would like to say some words about optimisations. So on this slide, we have a slightly simplified version of our first version of collecting application data for the application. So say that you have a header that says that we want we want so many bytes before it should be delivered. And then we come in to this read application data, and data is the newly decrypted data from the socket. And we have a buffer where we have data that we received before. And then we use the bit syntax and just append the data to our binary buffer. Very straightforward and simple to understand. and then we send it to the collect data function, and it has to check, okay, do we have enough data, or do we need to wait for some more data and calling this function again? So the problem with this is that we are potentially building many intermediate binaries at the increasing cost. So instead of queuing this way, we use an Okasaki queue with a twist. The twist being that we keep track of the size of the queue explicitly, as our elements in the queue are not of the same size. So I'm not going to show you the code for that, but I will explain how an Okasaki queue works. So the idea is that putting something into the queue should be just putting something at the head of the list, and taking something out of a queue should also be taking something out of the head of the list. So if we look at the leftmost picture here, we have a snapshot of an Okasaki queue with the size 6. And then this yellow person comes along and wants to enter the queue. So we enter him at the head of the rear list. And now we have a queue of size 7. So let's dequeue a couple of people. So when we have dequeued 3 people, the front list will be empty and the rear list will have the size 4. And in this situation, we just take the rear list and reverse it and make it the front list, and the rear list becomes empty. And this is the principle of an Okasaki queue. And if you don't need our twist, you can use our queue module that implements an Okasaki queue. And finally, I would like to say something about our current TLS 1.3 support. So in 23.0, released this spring, we officially support TLS 1.3, but it's not feature complete. And in 23.1, soon to be released, we will have enhanced session handling for all TLS versions. And for 24, we are not promising all the bells and whistles of TLS 1.3, but of course we will try to implement as many features as we have time to. And one of the big things is early data support. So of course we will continue to strive to make the user experience better without compromising security, because that is the Ericsson way and the OTP way. Thank you for listening.
Thank you very much, Ingela. And we have 10 minutes for questions, if I am not mistaken. You can post your questions to Vahuva for the session. Let's see, yeah, 16, 15. So I don't see anything right now, but like Jens datum is one of my favorite behaviors of all time. Perhaps my favorite piece of code ever. How many lines of code could you throw away when you switched from GenFSM to Jens datum?
Well, I can't really answer that on the top of my head, but yeah, we did throw away some code. We did. It became smaller, and it became so much easier to reason about. So TLS was what you call the beta tester, I would say, of the Jens datum behavior. And also the SSH application was also a beta tester. So both those applications were early adopters of Jens datum.
Yeah, and I guess the design happened very much open source, so people can go to the OTP issues list and look for the issue where they were developing the Jens datum and read an epic on how you design this kind of stuff.
Yeah, absolutely. We had a very long open source pull request discussion And I know that Raimo was sometimes frustrated, but in the end he was happy about it because the result was better due to it.
Yeah. There, we got a question from Andre Feton. Do you want to unmute your mic, or should I just read the question? I'll read the question. It's not a question at all. It's just a comment that says, thanks for the great presentation and introduction to TLS 1.3.
Okay.
I'll upload that.
Happy you liked it.
So we got another question from Karolis Pitusuakas. If you want to unmute your mic and ask your question.
Hello. It's interesting. How do you ensure the correctness of the implementation? Are you using property-based testing or maybe formal verification in some cases?
We do have some property-based testing, but it's we really like to get some time to do more advanced property-based testing, and I hope we can find some time to do that soon. We also have a commercial tool that we have tested it with. And of course, it's tested by a lot of open source projects. And we have test suites that I think it's like over 2,000 test cases now. Some test cases, of course, are run on lots of different configurations. So it's not like individual test cases. It's test cases run on the 2,000 comes from running them in lots of different configurations. So we test like with OpenSSL 0.09.8 D, I think, is the oldest, and I really hope nobody is using that. But from that to the latest OpenSSL, and we test on all kinds of platforms. And so we do our best, but of course we can always do more. And I think that we could benefit a lot from writing more advanced property-based tests.
Thanks.
So we have a question from Pia Anderson. If you want to unmute your mic.
Yeah, sure. Can you hear me?
Yes.
Indeed. Great.
So half a year ago, I was using our old self-signed C certificates, which are using SHA-1 with TLS 1.3. But the SSL application said then that there's insufficient security. And I researched this, and it doesn't seem like in the spec that I shouldn't be able to use SHA-1. I mean, it's not good, but there's nothing saying that I cannot.
Well, I don't remember all the spec in my head, but I think it's pretty much not. You don't want to use SHA-1 in 1.3, but there is this configuration parameter that you probably could change that could make SHA-1 applicable. You can ask me more privately and I can tell you which one it is.